Welcome to our monthly webinar series, Lunch with the NMSP, Food for Thought. This is webinar number 6 in the series. I'm going to take our little thumbnail videos away from the screen in the hope that doesn't show up in the webinar itself. So welcome again. Lunch with the NMSP, Food for Thought. This is webinar number 6, and we're going to be talking about pH and lime management today. As a quick introduction, my name is Corien Kettlings. I initiated and lead the Nutrient Management Spear program at Cornell University. Our mission is to help the farming community in the state of New York with the development of guidance and tools that can be used to improve crop production while also protecting the environment. Our motto is that we want to ask ourselves relevant questions, conduct sound science for agriculture profitability and protection of the environment. We have 6 focal areas in our program. The land grant responsibility is basically our responsibility as a land grant university and as a nutrient management sphere program to develop and support the implementation of land grant university guidelines for fertility management, nitrogen, phosphorus, potassium, sulfurs, lime, pH, all of that. A second pillar in our program is that we do research and extension programming on soil health and climate resiliency. We have a precision agriculture team within our program, a dairy sustainability team. We have the New York On-Farm Research Partnership, a network of farmers working on on-farm research with us. And the last of the list here is the student engagement. In our webinar today, we're going to zoom in primarily on a topic that's of relevance to pretty much all of this, but it falls under our land grant university guidance responsibility. We are celebrating 25 years of our program, started in August 1st of 2000. And as part of that celebration, we also decided to start with a webinar series. That's what you're listening to today. 5 webinars have already been held and completed. It's the first Friday of every month at noon. I started out with a webinar on dairy sustainability. We did one on adaptive nitrogen and phosphorus management. Then we learned about yield monitor data and on-farm research. And the most recent webinar was on the value and the power of manure. These webinars are all recorded and then posted on our YouTube channel, so you can access those after the webinars as well. The next webinar, just to announce that for next month, is on sulfur. Title is Let's Not Forget About Sulfur. And you can sign up for this webinar by going to the Spear Program events page and clicking on the registration there. It'll be again the first Friday of every month. Webinar today, going to be co-presenting with Manuel Marqueda. Manuel will be presenting on some of our grid sampling studies related to pH and lime management. I also want to recognize a whole list of people that have contributed to what you're going to see on the screen and hear about today in terms of pH and lime management, including Kevin Dietzel, Renuka Rao, and Sanjay Gami, the team that was responsible for development of a new approach to doing lime recommendations that we implemented in New York many years ago. I also want to recognize our participating farmers consultants in terms of the lime grid sampling project as well. And also on the screen are Suba Srinivasan and Ella Tular. Ella is an undergrad in our team. Suba and Ella have been working together on a new tool that is just posted this morning, and that we will share with you as well, a tool to derive lime recommendations. With that, we're going to dive right in. Here's the topics that we'll be covering today. A little bit of pH basics, setting rotation pH, soil sampling for pH, the basics of liming, so how does it really work? The concept of a buffer pH, which is a little bit confusing, and then how to derive a lime recommendation using the buffer pH. Talk a little bit about liming materials, and then the grid sampling project that Manuel will talk about before we wrap up. All right, the basics. The first slide here is one that I took from our webinar from last month on the value of manure. What do crops need to grow and produce? We're all familiar in agriculture with the nutrients that a crop needs. We know they need light and water, and oxygen and some heat, some temperature. But we also need to recognize that proper pH is on this list. And actually, it should be one of the top items on a list for crop production. We're going to talk about pH management and how important it is and how we do this. So that by the end of the webinar, you hopefully will fully be able to understand and derive recommendations. So on the basics, pH is a measure of acidity. And the units can go from 0 to 14, with 7 being neutral, a neutral pH, not acidic, not basic or calcareous. Basic and calcareous is the same wording. The way that pH the units are shown is in logarithmic scale. So 1 unit of change in pH means 10 times more acidity in that soil. So a pH of 5 is 10 times more acidic than a pH of 6 and 100 times more acidic than a pH of 7. Just the way in which this is noted. pH is a logarithmic scale. It's a measure of soil acidity. Anything below 7 is called acidic. Everything above 7 is called basic or calcareous. There's some reasons why we want to focus on pH, and that is because it helps our crops grow better. There's a couple of reasons here on the screen in terms of why that could be the case. The first one here is one that's well known. It increases the availability of essential nutrients. When we manage at the pH between 6 and 7, most of our nutrients would be at their max availability. Lime material can supply plants with calcium or magnesium if needed. It can improve soil conditions for microorganisms. They like a certain pH as well. It can increase effectiveness of some of the herbicides and improve soil structure. I want to zoom in on the soil conditions for microorganisms for a minute. And for us in agriculture, that's important because of our legume crops. Our legume crops are able, in a symbiosis with bacteria, to fix nitrogen from the air. They can fix N2 and turn it into a nitrogen supply for themselves. So these legume crops don't need to be fertilized with nitrogen fertilizer. Especially in the current climate, that can save us a lot of money. So no need to apply nitrogen fertilizer to legumes, soybeans, alfalfa. But if we don't manage the soil at the proper pH, we can impact this ability of these bacteria to fix nitrogen. So if the soil pH is below its target pH of 7 for these crops, less nitrogen will be fixed. And lower pH for these crops means that the yield could be impacted as well. The big message here is investing in lime is a much cheaper way to go than to invest in nitrogen fertilizers. The crop will grow at a lower pH, but if it doesn't fix nitrogen, it's going to cost us a lot more in terms of fertilizer dollars to grow that crop. So this is a main reason why we have to pay attention to soil pH for these particular crops. I want to share some results of some studies we did a while ago. Here's the results of soil pH measurements for 45 alfalfa fields. These are alfalfa fields, target pH of 7, minimum pH of 6.7. And the distribution here shows that 60% of the fields that we sampled, a random sample from the state of New York, 60% of those fields had a pH below 6.7. The rest was above 6.7, and only very few were above the target of 7. 8 of those fields were above 7. There were a number of fields between 7 and 6.7, and then 60% below a pH of 6.7. And we did some yield measurements for these fields as well. These are all alfalfa fields. The average yields of these lower pH fields was 16% lower. So we're giving up yield by not properly managing pH for those higher pH fields, alfalfa soybeans. So we know our pH is important. How do we determine what our pH is and how we set a rotation pH? This is a list of crops that we commonly might be working with in field crops within the state of New York. And it shows two levels here, a desired pH and a minimum pH. The target for a rotation, when you have a particular rotation, you want to make that target the minimum pH for the crop that needs the highest pH. So set your target minimum pH based on the crop rotation, and it's set by the minimum pH of the crop that needs the highest pH. So if you have alfalfa or soybeans in the rotation, your target pH is the minimum pH for those two crops. And you see that at the bottom here, the pH of alfalfa soybeans, desired pH of 7, minimum pH of 6.7. The difference between a desired and a minimum pH is that, if you're under desired pH, not a big a deal to skip lime for a year. But if you're below the minimum pH, it is time to start applying lime for those fields. All right. So the minimum pH of the crop that needs the highest pH is what your target is set at. So, okay, we know what a pH is. We know how to set a rotation pH. Now, let's collect some samples. How do we sample for soil pH? There's multiple reasons why we want to soil test, and we will come back to this in a future webinar within this series. But I wanted to point out the number one reason here on the list to determine soil pH and buffer pH to guide lime management. There's no other way to do this than to actually get a soil sample and a measurement taken at this stage. So we need to determine soil pH and buffer pH to guide lime management. In terms of depth, we have a couple of different depths. Most conventionally tilled fields will have a sampling depth of 8 inches. So our recommendations based on a sampling depth of 8 inches. Pasture fields, that's a no-till situation. The recommended depth is 0 to 6 inches. For no-till or minimum till, we make it more complicated for a good reason. For no-till or minimum till, we would recommend taking 2 samples, the surface 1 inch, and then the 0 to 6 inch sample as well. So 2 different samples from the same fields, from the same spots. The reason why we do this in terms of no-till or minimum till situations is that we want to capture in time when the soil pH is beginning to drop at the surface. Because in no-till and minimum till situations, we cannot incorporate the manure, we have the surface supply. And that means it takes much longer for that lime material to mix with the soil and change the pH. So it's a timing issue. If the surface pH is too low, so if the surface pH, meaning the 0 to 1 inch layer, is too low, but the pH of the 0 to 6 core is okay, you do want to add some lime to get that surface layer back up to where it needs to be. If the surface pH is okay, but the lower pH, the 0 to 6 inch core, is too low, you can see in terms of the first inch is okay, but it's time to start liming because the rest of the profile is dropping below the target. And if both of these samples are below the target pH or below the minimum pH, you might not want to use no-till methods for the establishment of legumes. You might want to also consider maybe another crop in the meantime and slowly build those levels. There's a couple of things in terms of soil sampling to also keep in mind. There is seasonality in pH. There's an example of samples we took starting in May, and then June, July, October, November, and then the next April. And the bars are the pH levels. This is across 20 fields that were summarized on average. Across pH levels, you see a dip in pH. There was a dip in pH in June and July, primarily reflecting that in those months we tend to have lower moisture content than in other areas of other times in the season, and higher temperatures. So you want to recognize that seasonality happens. So if you want to see if your pH is changing over time, the recommendation is to sample roughly around the same time of the year. So if you sample in the spring, the next time come back and sample in the spring. If you're sampling in the summer, come back in the summer, so that you can rely on these longer term records a little bit better. Another thing with timing of soil sampling, and this goes back also to the no-till scenario. As water flows through the profile, lime will be carried downwards, and it changes the pH from the top down. That process can take a long time. So for rotations that include alfalfa and soybean with those desired higher pHs, and where there's a big lime difference, lime should be applied at least 6 months before seeding. So the ideal scenario is that you would apply lime in the spring before alfalfa or soybean is planted the year before to ensure that the pH is optimal in the seeding year. So we're not liming just before we plant alfalfa. You really want to do that in your last year of corn to make sure that the pH is back up to where you want it to be when the new seeding goes in. To lime at least 6 months in advance. There's a couple of other considerations here also. There is such a thing as too much lime. So when the lime requirements are greater than 3 tons per acre, you want to split that application, plow down half of it, work the rest into the surface. If you have a recommendation that goes over 6 tons, you really don't want to apply that all at once. You want to apply a smaller amount during that rotation and split apply and then test again in 3 years and work it to its desired level over time instead of trying to do it all at once. The negative impact of applying too much lime material at once is realistic. It will lock up nutrients and have other side effects that are not desired. There is a fact sheet in our fact sheet series. It's the one that's on the screen right here, where we talk about the timing of lime application for field crops, and you also see that figure in here with the information on what happens in terms of seasonality of pH and a little bit of an explanation as to why that would happen. All right, so we know the importance of pH. Now how to set a rotation pH. We know some information about proper soil sampling for a pH measurement. Let's go into the basics of liming itself. I want to start that out with talking about liming products and the definition of liming products. It's a product whose calcium and magnesium compounds can neutralize acidity. The wording here is really important. It's a product whose calcium and magnesium compounds can neutralize acidity. It is not the calcium and the magnesium that neutralize acidity. It's the rest of that material that does the neutralizing. And we'll come back to that in the next slide. The neutralizing value of a liming product is expressed as its calcium carbonate equivalent, or CCE. And that's basically the neutralizing ability of that particular liming material compared to pure calcium carbonate. It's a way that it's noted. It's an agreement among the industry that's the way we show quality products, by expressing it in terms of calcium carbonate equivalent. And that calcium carbonate equivalent of a liming product has to be listed on the sales tax. That is a requirement by the state of New York as well. All right, so liming products are products whose calcium and magnesium compounds can neutralize acidity, and we express them as calcium carbonate equivalent. So how does this work? The image here on the left, you see acidic soil and neutral soil. Let's start at the top left. Acidic soil is a soil with H plus and aluminum 3+ on the exchange surfaces of the soil particles. You see that in the schematic here. So you see H plus and aluminum 3+ on the surface of this acidic soil. If I then add calcium carbonate, calcium will dissolve, the calcium carbonate will dissolve, and the calcium out of the calcium carbonate will displace hydrogen and aluminum on the surface of the soils. So now we have calcium on the surface. We've neutralized that surface area. And we have H plus and aluminum 3 plus in solution, in the soil solution. Now it's the carbonate out of the calcium carbonate that does the neutralization step. So the calcium displaces the H plus and aluminum 3 plus, and the carbonate is what neutralizes that acidity. It forms aluminum hydroxide, CO2, and H2O. And the aluminum hydroxide is a neutral compound. CO2 is neutral, H2O is neutral. So now we have increased the pH because we took the acidity out of the soil solution. And this is how liming products work. The calcium or the magnesium will replace hydrogen and aluminum, force those two into solution, and then the compound that's attached to that calcium or magnesium will do the neutralization step. All right, so we know the basics of how liming works now. How do we now actually derive a lime recommendation? And here's where the concept of buffer pH comes into place. So the pH is a measure of active acidity, and it tells you if you need to apply a lime. So if the pH of your field is less than your target pH, you know, okay, I need to start liming. It is the buffer pH that tells you how much lime you need. And on a soil test report, like the example here, you will often see those two listed, soil pH and buffer pH. It's two different data points on your soil test report. It gets confusing. You might ask, like, which pH do I need to lime to and stuff like that. And that's a part that is a little bit unfortunate in terms of the use of the word buffer pH, but I'll hopefully explain how that works. So let's take a look at why we need to know buffer pH. Here is a coffee pot, one of these big coffee pots. It has a lever. I don't know if you can see my cursor. There's a lever on the side that you can tap the coffee from. Okay, let's imagine this coffee pot represents your soil. And we have two of these coffee pots. The one labeled A is a bigger coffee pot, and it has the lever, and the lever is showing the pH level. Coffee pot B is a much smaller coffee pot. It also has a level, and it says pH, and it's at the same level as soil A. So we have two soils, soil A and soil B. The reserve acidity or the buffering capacity is the content of the coffee pot. Now, if I have soil A and soil B, which one of these two do you think you need to apply more liming material to increase the pH? You can use the chat. What's your answer, A or B? Which one of these two soils needs the most lime to increase the pH? Anybody dare to guess here? Okay. I have a B and a couple of A's. So if you take the volume as your soil and you want to increase the lever, the pH, you will need to put more into soil A because it has a bigger volume. Right? We need more coffee into soil A to reach to elevate the pH level in the lever. So A is the right answer here. You could flip that around also and say, if I stop tapping and taking out coffee, which one will drop down the quickest in terms of reserve acidity? And that would be coffee pot B, soil B. Now, if we translate that back to soils, the soils that are like coffee pot A here are the heavier soils, the clay soils, that have a higher cation exchange capacity, more organic matter, and they will need more lime to increase the pH. The coffee pot on the right can react really quickly. A little bit of lime will quickly increase the pH. Those are the sandy soils, lower cation exchange capacity, lower organic matter, and lower lime needs, but they also will need more frequent lime additions. If I did not know the size of the coffee pot and I only had the pH level, would I know how much lime I needed to put in to increase the pH? And the answer to that question is no. If I don't know the size of the pot, I do not know how much lime I need to apply to increase the pH. So your buffer pH is a measure of the size of the pot. Your buffer pH is what tells us how much lime we need to add. And that's why the buffer pH is on your soil test report. What does that look like? Well, just before we go into the interpretation table, I want to explain that buffer pH thing. Before 2010, when I arrived at Cornell in 2000, and then the first 10 years, the recommendations were based on an actual measure of the exchange acidity using a standard methodology, a barium chlorate TEA titration. It works very well, it's very accurate, but it generated toxic waste and it was incredibly time consuming. So there have been various attempts to derive a buffer pH method that is easier to do, quicker to do, and does not generate toxic chemical waste. And we did a study back in 2010, 2009, to compare a whole bunch of those buffers and to make a decision about which one is the best for us to use. And what we ended up doing was transition to the use of what is called a modified Mehlich buffer pH. That's even much more confusing because now it could be confused with the Mehlich extraction for soil fertility. It's the same person, but that's the only comparison there. This modified Mehlich buffer pH is what we now report on our lab report. Forget the name. The only thing you need to remember there is that it is a buffer pH. And actually, it would be much better if you just imagine that this is not buffer pH, but buffer capacity that should be measured. So the buffer capacity measured as buffer pH is what's on your report. Think of it as the size of that coffee pot. All right, now we know what we need to sample. Let's derive a recommendation using that buffer pH. So to determine the lime needs, initial pH compared to the target pH will tell us if we need lime. The buffer pH can then be used to determine how much lime we need. And to determine that, all we need to do is look up this table. So here we have lime requirements. There's modified Mehlich buffer pH on the left. This list goes from 5 to 6.6. It does not go over 6.6 because the original solution has a pH of 6.6. And then there's 4 columns for the target pHs. So on the right, the target pH of 6, that's for corn silage, corn grain crops, and grass crops. On the left, the pH of 7, that's what we're striving for alfalfa and soybeans. So this list here, we can simply read off the number based on what our buffer pH was and what we are liming towards. The table itself assumes tillage depths up to 7 inches. If you have 8 inches, you multiply it by 1.33. If you have 9 or more inches tillage depth, you multiply by 1.67, simply recognizing that that's a bigger volume of soil that you want to increase the pH for. But a couple of examples here. Current pH, 5.5. We have a rotation with corn silage, COS, corn silage, and then alfalfa grass, AG, first establishment, and then the top dressing years. The buffer pH is 5.8, the tillage depth is 6. How much lime would I need? So to answer this, our first question is, what is our target pH? If you want to participate, put in the chat what your target pH is for this rotation. Rotation of corn silage and alfalfa grass. Excellent. 7. We're going with the column that says 7 because we are targeting the highest pH loving crop, which is alfalfa. Now our buffer pH is 5.8. Look at the 5.8 and I look at the target of a desired rotation pH of 7. What does it say in terms of how many tons of lime do I need? 4 tons, exactly. We're simply reading off the table. We can do that for other examples also. The next example is one where we have corn silage and grass. So just pure grass. Target pH for this would be 6. The rest of the information is the same. So I look at my buffer pH of 5.8 and move over, and I see that my lime recommendation for this scenario is 1.5 tons. For those that grow cash grain crops, I have a corn grain, soybean, wheat rotation. Here we also fertilize to the highest pH. We lime to the highest pH, and in this case it's soybeans. So here we are back to liming to 4 tons per acre. All right. There are some fact sheets here too on the buffer pH that has the information about desired and minimum pHs and the lookup table for lime recommendations. You have a calculator as well that allows you to put in some numbers. It's an Excel spreadsheet that you would need to download from our website with fillable boxes to try to come up with that same 4 tons of lime here in this example. All right, a little bit about liming materials. So you've derived a recommendation. Let's say, it's 4 tons per acre. The next question is, what liming products do I need to use? As I mentioned, the liming product is a product whose calcium and magnesium compounds neutralize acidity, and there are various options. New York has rules and regulations. There are some quality standards that need to go along with any product that is sold under the header of a liming product. It has to have a certain percent of calcium carbonate equivalent, at least 60%, and it has to have a certain particle size distribution. All of these sources can increase your soil pH. Some are more expensive than others, some are quicker than others. They have their own calcium carbonate equivalent. It's not one is better than the other, it's just different. So calcium carbonate is a calcium carbonate equivalent of 100 by definition. Magnesium carbonate, 119. Dolomitic limestanes are the calcium magnesium carbonate are 109 calcium carbonate equivalent, just different. Now the neutralizing value, neutralizing ability of these liming materials, for a given amount of acidity, an equivalent amount of liming material will be required regardless of how fine you pulverize that liming material. But if I take a big rock of calcium carbonate and I dump it on my backyard in the hope to increase pH, I need to be alive for numerous lifetimes before I see that change in pH, right? That rock here is not going to dissolve very quickly. So the speed of that liming reaction will depend on how fine the material is ground. And that's why we have fineness as a measure in liming materials quality. The fineness is measured as mesh sizes, so the number of wires per square inch is a mesh size. The higher the number, the finer the material. So you can see in the figure here on the right, 200 mesh is powdered stuff, 100 mesh is very fine as well. If you go all the way up to 1/2 inch mesh, that's rocks. So the fineness determines the speed of reaction. The finer, it will react faster, but there are practical limitations. You can imagine if you have like powdered material, it might be difficult to apply. It might blow away in the wind. Grinding does not change the calcium carbonate equivalent of the material. So the quality of the material stays the same. The chemical composition stays the same. What changes is the speed of the reaction. And that is symbolized in this as well. Here on the x-axis is the timing as a function of pH increase. You see the 100 mesh, which is the finer material, will more quickly increase the pH than materials that have a mesh size less than 20 that really don't do much in terms of changing the pH because those particles are too big to dissolve in a reasonable timeline. How do we determine fineness? We basically have to have 2 mesh sizes, the percent passing 100 mesh and the percent passing a 20 mesh. And those 2 things are required by state law as well to be recorded for every material that's sold as a liming material. So we take the percent passing 100 mesh and we look at the difference with the 20 mesh, that fraction, so between 20 and 100, the larger particles, are multiplied by a fraction of 0.6, recognizing that not all of that is going to benefit us. The stuff that passes the 100 mesh, the finer material, is 100% credited. And then we add those two together and divide by 100. And here's an example of a calculation here. 97% passes 20 mesh, 70% passes 100 mesh. The difference is 27. 0.6 times 27 is 16. We add to that the 70% that passed the 100 mesh, gives us a score of 86. So our finest factor is 0.86. And that's how it is determined. As long as you know those percentages passing 20 and 100 mesh, you can do this calculation. All right. Now, we need to bring the calcium carbonate equivalent and the finest factor together. And that is done by introducing another concept of effective neutralizing value, ENV. So ENV is calcium carbonate equivalent multiplied by that finest factor that we just calculated. When you send in a soils report and you ask for a recommendation for a particular rotation, the results that come back are in tons of 100% ENV, because the lab doesn't know what liming material you are working with. So it's standardized for 100% ENV. In this example, 3.5 tons of lime was recommended for this particular rotation. If I then work with a particular liming source, I have to take that ENV into account. So here's the same recommendation. If I have a liming source with an ENV of 70, I need to apply 3.5 divided by 70 times 100 is 5 tons per acre. This is really important because if you don't adjust for the ENV of your material, you will likely under apply your liming source. Most of the liming sources have an ENV less than 100. So when you get from a lab a recommendation, it needs to be converted to an actual rate depending on what sort of material you're working with. I mentioned up front, we have a brand new calculator. This is what it looks like that allows you to do these calculations. And I have a quick demo for that as well. It was just posted and it will go through a few more tweaks before we finalize it, but it's up on our website right now. So here's a quick demo of what this calculator can do for you. The URL is at the top of your screen here. We can enter some farm information. And then we have 6 boxes for the actual rotation. So we can select from a drop-down menu what crops we want to have in our rotation, or what crops we have in our rotation. And based on that, the software is going to pick your rotation pH, just the exact same way as we talked through just before. This calculator will then let you know if you need lime, depending on the pH that was entered. So in this case, pH was below the target pH. So the software says, yes, you do need the lime. You enter the modified Morgan buffer pH, the modified Mehlich buffer pH, sorry. That's where it's confusing, the buffer pH, and the tillage depth, and it will give you a recommendation. This calculator also on the right allows you to play along with a couple of different lime sources and try to pick the one that is most cost effective for you. So you can enter the quality information like either the fineness or the ENV and do a comparison of multiple sources and then identify which one you want to move forward with in terms of liming of the fields. And then based on that selection, it will allow you to identify how many acres you have in a certain field, and then it will give you the total cost involved with that, the total amount of liming product needed. Brand new, just uploaded. One more slide before we go over to the grid sampling. I get questions about what is better to use, dolomitic or calcitic limestone. Those are the 2 products that we typically use in field crops. The difference is that dolomitic limestone contains calcium carbonate and magnesium carbonate. So it has some magnesium in it. And if your soils need some magnesium, that would be the better option. Technically, dolomitic limestone would react somewhat more slowly than calcitic lime, But as you can see in the chart on the right, if you grind it fine enough, that difference disappears. So the difference is really minimal, given that we are talking about a lot of products that have somewhere around uh, this mesh difference. You want to basically, if you don't need the magnesium, choose the most economic liming material when lime is required. That's the bottom line of that message. With that, I'm going to hand it over to Manuel to briefly talk about our grid source sampling project.
Hello, everyone. Can you all hear me?
Yes, we can.
Good. I hope you all are enjoying your lunch. On to our grid sampling project. So this project was implemented over 6 farms across central, western, and northern New York, and a total of 20 fields. The grid sampling was done at the half an acre resolution. And in the intention of showing the or comparing the differences if we have it in larger grid samples, we extrapolated the half an acre, the original sampling of half an acre. We extrapolated them into 1 acre, 2.5 acres, and of course for the whole field level. And we do this using the area weighted average. Um, just to show you how variable the fields are in terms of the represented soil series, this plot here shows you on the y-axis the name or the codes of the fields that we sampled, and the length of the bar is telling us how big the fields are, and our fields are fairly representative of a common field in New York State. We have sizes ranging from 10 acres, and the largest is 142 acres. And you can also notice that for each field, there's at least 2 to 8 or a maximum of 8 soil series that are represented in a field. So, okay, let's go back. Oh, Karine, can you help me go back? Ah, there you go. Okay. Um, oh, all right. Um, so we calculated the pH and the recommendation for every field that we sampled, and we followed the recommendation that was discussed by Corinne earlier. And you can see on the plot here on the leftmost part with a lot of dots. We're showing you here the range of soil pH that were measured in a field. The horizontal line is the length is the range of pH, and the dots is the whole farm weighted average, whole field weighted average pH for that specific field. And as you see here, um, most of the fields are above the desired. Oh, by the way, we analyze them for two crop rotation or target pH, the 6.2, which is for the corn, and 7.0, which is for soybean and alfalfa. And most of the fields that has a target pH of 6.2, their whole field average are mostly above the required. And if you go and determine the whole field average lime for target pH 7.0, you will notice that there are a few fields that are above the desired, but a lot are below the minimum or below the desired um, pH recommended below the desired pH. Um, this just tells you here. I mean, sorry, I have to go back as well. Sorry. The bar plots on the right is showing us how we classified the field into different levels of pH. We classified them below minimum, within the desired, and above the desired, which are based on the target pH for your objective. And the colors on the bars represent how much or what's the percentage of the uh, field is represented by that pH level or pH classification. And the number that you see, or the percentage that you see on at the end of each bar, tells you how much lime, the percent, or the percent of the field that needs to be limed. And you can see how variable the fields are. And we were able to capture different levels of or classifications of pH within the field. And the next slide here, uh, the sample maps tells us where those classifications are. And you can see from left to right the whole field classification up to the finest classification, which is in half an acre grid resolution. And if you notice, this is actually a contrast of two things, or the pH 6.2 and 7.0 are kind of contrast of in terms of the how these how the recommendation will be applied on these plots. So for example, on the topmost, the fields A3 and A1 at whole field level, they are on the above desired level of pH, which means they probably don't require um, liming at the whole field level. But if you go zoom in to finer resolution, you will identify parts of the field that will need some liming. So that's for target pH 6.2. In contrast, if you go to pH target 7.0, oh, so sorry, I said it in reverse. If you are above desired, you don't need to apply lime, but zooming in to smaller grid resolution, you will identify that there are some parts of the fields that need liming. At target 7.0, at whole field level, the recommendation, or the pH level is below minimum, which means that they need to be limed at whole field level. But if you zoom in, you will also identify at the finer resolution that there are areas in the field that actually don't need liming. So what I'm telling you here is um, liming or grid sampling could cost or save you some materials. But if it costs you something, the upside of it is you're able to identify areas of the field that needs attention and would potentially, if you attend to those areas in the field, it would help you increase your yield. This is a more detailed comparison of all the fields that we examined, where we wanted to see we wanted to compare the recommendation at the whole field level with the grid sampling. So if you will notice at pH target 6.2, about half of the field doesn't have the same recommendation as with the whole field lime recommendation. But you will see for some fields that as you go on grid sampling, it would actually cost you um, some some lime or some lime materials. And for pH target 7.0, more fields needed some liming, which would cost you some lime materials. But if you also take a look at field A1, which is also on the map right here, we are able to identify some areas or some savings as represented by the green circles here at uh, at the finer resolution. So your grid sizes can impact your savings and cost depending on how variable your field is. If you want to know more about this research, we have an extension article that you can read on, and it's also published on a journal. Both of those of the copy of those can be scanned through your QR codes and read through them in detail. Corrine?
All right. Thanks, Manuel. So wanted to come back on the definition of pH. I mentioned it was a logarithmic scale. And that has consequences. So great advantages of grid sampling if you have variable fields and you can manage at that within field level. But if you then want to come back and resample for pH, or you want to have a full field average pH, you gotta recognize that you cannot just add up all the pH values, take a average of that. Because of that logarithmic scale, you have to convert it back to the concentration of hydrogen ions before you can do an average of those grid cell samples. And that's what this example here on the right is showing. It has listed a number of pHs for particular grid cell sizes that were sampled. We need to convert it back to H plus activity, then average that, and then convert it back to what that means in terms of pH terms. If you don't adjust for that, over logarithmic scale, and you don't take the grid sizes into account, you took just an average of all these pH values here, you would have gotten the incorrect value of 5.9. By taking into account the logarithmic scale and the grid cell sizes, we come to an accurate pH of 5.3. So that would be something to take in mind if you have grid sample results and you want to combine that into a field size average pH. You have to go through a few calculation steps. This fact sheet here is helping to explain that in terms of averaging across these grid cell sizes as well. So you can read more detail here in this fact sheet. With that, we've come to the end of our webinar. Some take-home messages. pH management is key for crop production. We do give up on yield and we increase our fertilizer reliance if we don't manage at the proper pH. Soil pH and the target pH will tell you if lime is needed. I should emphasize also target pH is a minimum target pH. There's no problem at all with a pH of 7 for a cornfield. It's a minimum target pH. We don't want to be below it. The buffer pH, or actually think of it in terms of buffer capacity, is the size of the coffee pot. It tells you how much lime we need to use. But you do want to adjust the rates that you're getting for tillage depth, but also for the actual liming source that you might have. The neutralizing acidity of a liming product is expressed as calcium carbonate equivalent, CCE. Smaller size particles react quicker, so we have a fineness factor in that as well. And the lime quality is then expressed as effective neutralizing value, or ENV, which is simply the multiplication of calcium carbonate and fineness factor. Lime recommendations that you get from a laboratory are always assuming 100% ENV because that lab does not know what liming sources you're working with. You do have to adjust that for the ENV of the actual liming material that you have access to. If you don't do that, you will be under liming. You will be applying not enough. If you have a high pH crop in your rotation, alfalfa seedings, for example, or soybeans, you want to start monitoring your pH in time because it takes time for that liming product to work itself into the soil, especially in reduced till and no-till situations. If you need high application rates, it's better to split those applications. And if you're coming back with a recommendation of 6 tons of 100% ENV, don't apply 6 tons of 100% ENV material. You might actually opt for growing a different target crop to build the pHs up over time. Grid soil sampling is effective in identifying areas that have variability in pH and identifying where you can either save yourself some money on lime or actually benefit your crop productivity by putting in some lime. So it could address both the yield barrier and help you save money in other places. We have a couple of resources on our website. On the right is our line guidelines for field crops document for the state of New York, and on the left is our fact sheet series, and we highlighted several of our fact sheets throughout the session here today. And with that, we want to thank our funding organizations who have supported us over the last many years as we were working on grid sampling, developing the buffer pH approach for the state of New York and things like that. And all the participating consulting firms for particularly the grid sampling and for also the collection of soils that were part of the study on deriving Lyme recommendations. I want to also announce the next webinar. Our next one is going to be all about sulfur, and that's going to happen on June 5th.